Okay, so this is, as I previously said, this is the first webinar that we'll be running weekly. So we'll be running weekly webinars all the way through until April. And just to give you an outline of what we've got planned, this is our program. That next week we will have a talk by Professor Pete Smith from Aberdeen University on his project. Unfortunately, you'll need to register for each of these events separately, and you can find links to do that through our website, which is the Greenhouse Gas Removal Program. And if you look under latest news, you can find links to the register. You can follow us on Twitter at UKGGR Program, or if you can't find the registration links, then do contact me or follow me on Twitter, and I'll be tweeting the links before the event. So do please engage with the webinar series. I'm really excited to present this for you. So just a bit of background, the GGR program is an £8.5 million research program that's funded by the UK Research Councils, mainly NERC, EPSRC, ESRC, and the Government Department BEIS. It funded 11 projects in 2017, and many of those are still ongoing, sort of coming towards the end of their lives this year. And I suppose this webinar series is an opportunity for you to hear about the outcomes of those projects directly from people who've worked on them. So our first webinars, we're delighted to welcome Professor Simon Tett from the University of Edinburgh. He's a chair of Earth System Dynamics, and his interests include generating and running plausible climate models, looking at extreme climate scenarios and events. And he's the principal investigator for the MERLiN project, which stands for Metrics for Emissions Removal Limits from Nature. I hope I got that right. Yeah, it's on the screen there. So yeah, thanks Simon for agreeing to come and give a talk. I'll stop sharing my screen and you can start sharing yours and you can take it away.
Thanks, Phil. Let me see if I can do. Here we go. Can't see you anyway. So this is a presentation on the work we've done in the MERLiN project. MERLiN, the name was chosen slightly tongue-in-cheek to capture a little bit of our skepticism about greenhouse gas removal. The sense it was a technology that didn't yet exist, but was needed to get us to zero carbon. So that's kind of, I mean, the name, of course, in classic Research Council way, was made to fit the abbreviation we wanted. We're mostly based, in fact, we're all based in Edinburgh. I think we're one of the smaller projects. So I'm the PI, Viv was the postdoc employed on the work, Matthew Brander is the co-I, and then Mike Miniter and Andrew Schroer are our colleagues in the School of Geosciences who provided various bits of help. So the talk itself is essentially two papers brought together, one that's been published and accepted, but one is still a bit under development. So essentially, the first one is about accounting issues for negative emission technologies, and that was work led by Matthew. I think he's here. I can probably answer some of the questions, but tricky ones I will divert to Matthew. And then the second one, which is about consequences of overshoot. There are some surprises in that. So that provides food for thought, I think, as much as anything else. So let's start with carbon accounting for nets. So there's a lot of mention of accounting for nets in the literature and the sort of policy world. So reliable accounting of net carbon emissions is necessary for carbon CDR, carbon drawdown to work, and for policy makers, investors, and the public to support it. On the practical side, so we need to be able to reliably account for these net carbon emissions. On the practical side, these knowledge gaps are also associated with the current lack of consistent emission accounting rules for all types of nets. And integrating greenhouse gas removal into policy raises lots of challenges relating to uncertain costs, side effects, life cycle effectiveness, and accounting. So essentially working out the CO2 emissions and drawdowns and when and where. But there's a limited systematic overview of what was needed. So Matthew led this work. And essentially this is a sort of focused literature review. So it began by some keywords in Google Scholar, which found a bunch of papers. Those papers were screened out, so remove the ones that are not obviously about nets. And then the snowballing search, that is, find the literature that cites the ones you found. Papers and approaches coded fairly subjectively, the sets from the data as it comes in, rather than beforehand. Found 55 papers from that. Also searched in response to referee comments, life cycle analysis, and found 51 papers, but there was no new accounting issues. So essentially this is a systematic literature survey and a kind of summary of what the literature reports. It's useful, and again, that I think it makes us, should make us as a community think harder about what we're trying to do. So the first thing that comes out is the importance of a baseline. And the magic story here, or the story here is you need a counterfactual baseline, because that's, what would happen in the absence of the change you're making to generate nets. That baseline is unobservable. You can't monitor it because it's not happening in the real world, and it therefore needs to be modeled. And here's a little schematic of us. Here we have some time in years. Here we have what our counterfactual is, our baseline carbon stocks, so they're increasing. Here is the observed carbon stocks with the change that we've made to get nets. So no, they're also increasing, but the difference is negative. That is, our change has actually net reduced the amount of carbon being stored. And so that's the one importance about having a sensible baseline to compare with. You can't just monitor. Matthew told me that this was important and I needed to stress it. So hopefully I manage it. So the issue is attributional life cycle assessment via consequential life cycle assessment. So attributional will be to consider only the carbon changes from whatever system you're thinking about. So for example, for BECCS, we might count carbon emissions from biomass harvesting, carbon used to capture the carbon, transport it, and inject it into long-term storage. So we'd work through that budget and add everything up, etc., etc. That's okay when small scale, but CO2 emissions are planetary scale. So all greenhouse gas removal technologies will have to be deployed at planetary scale. So one thing is for people to think about the consequences of having that technology deployed on a planetary scale. And consequential is that there are knock-on impacts via markets and prices. So you can't just add up all your own stuff and forget about the other consequences through markets. So for example, BECCS, personally I think BECCS is a silly idea, but hey. Increase of biomass, which BECCS will cause an increase in land use change through market mediated demand. So that in turn will change the stocks of carbon dioxide, or particularly carbon, in particular, how much is in the land versus how much is in the atmosphere. And stuff in the atmosphere is what we in some way care about. If BECCS CO2 is used to enhance oil recovery, then even if you included the carbon you'll get lower oil prices, and that will increase carbon use. And so you need to think about that. So I think a lot of attributional stuff, which will occur through pricing changes or market changes, will essentially require economic impact to try and estimate what that is. And because to make these technologies work, they have to be deployed on planetary scale, I think we need to think about their impacts on planetary scales. Does that all make sense? Let's see. Okay, non-permanence is a big deal. So where is the carbon from negative emissions stored? So for example, if we think about land use change, growing more forest, which I think is partly the UK strategy. That's not very permanent. It can be, we can get wildfire. So here's an image from the Australian wildfires of early 2020. 2020 was not a good year. We avoided at least the war horsemen, but we had fire and disease. So here, that's just an example. So the forests themselves aren't really permanent stores of carbon. So you can solve by recapturing the carbon with time, but even in, say, managed forests which don't burn, you might have harvesting, you might have disease. So worth thinking about all those issues. And so here's a schematic of this. So we imagine we've got some, so we start, so these are emissions and removal. So when planting takes some energy, we might disturb the soil and emit carbon, we might need fossil fuel to plant them, whatever. So we basically get an emission. If we then think about the cumulative net emissions, so then our trees are growing. We might take some annual removals from trees, we might harvest as we go along a little bit, but so essentially we get in this case of trees, we get a rather rapid shift, draw negative emissions as we get to sort of final stage. And then we harvest these, we then plant, we then need to, we have to process and replant, so there's sort of carbon emissions. So we turn the wood, and we might turn those into hardwood products, wood products. So we have a positive emission because we've got harvesting, process, and replanting, and then we plant again, draw down. So that's looking good. But then, well, what happens when the wood products reach the end of their lifetime? That's some more emissions. So that's a pulse. We then do another planting, and so on and so on. So you can see, at least in this simple model, that actually might be consequential. Long-term positive, certainly not negative, might be positive, because essentially the end, wood itself has some kind of lifetime. So that's, and I think it's a point they've made in a paper we published, well, he published something back in 2013, that I think it is important to think about the lifetime of the carbon store. And trees aren't particularly long-term, deep ocean is better, geology is very long-term. Okay, incentives. It's important to account for carbon correctly. And so an example might be bioenergy. So currently bioenergy is seen as zero emissions. So that was captured and then just burnt, but not counted, but it wasn't counted when harvest because of not being included in that country's nationally determined contribution. So the issue there is to use the reality principle, emissions and removal counted when and where they occur. So in this case, the removal would be counted in the country when the trees were planted. There'd be some emissions when the trees were harvested, because there would be some soil changes and so on. And then there would be a bunch more emissions when they're burned. So that's a point about using the reality principle. We count emissions and removals when and where they occur, in both in time and space, if we're going to do it at the national level. So summary and recommendations from this. Consider permanence. How long is the store? I'm going to show you in a bit that overshoot has consequences. So see you later about that. Use the reality principle. That is, think about carbon emissions and drawdown as and when and where they occur. Use a consequential life cycle analysis. Nets will need to be deployed on planetary scale. So we'll have planetary scale side effects through changes in pricing and markets, and these need to be considered. Okay, so I'm now going to look at essentially consequences of overshoot. So Paris, our goal was less than 2 degrees and ideally 1.5 to essentially reduce the risks and impacts of climate change. I think largely through extreme climate extremes. And people think, well, we're not going to be able to get to 1.5. We're already basically at 1.2-ish without some overshoot. And so we're going to have some negative emissions to pull this down. So one of the question that MERLiN was asking is, well, what are the consequences of this? and so we're going to have some negative emissions. So we simplify this in MERLiN in our case. Well, let me just also talk about the big idea. So the one interesting idea, as I put it, from the last IPCC report in 2013, didn't really see anything different from anything else, was this linear relationship between cumulative total anthropogenic CO2 emissions and climate response, with very broad uncertainties which depend on model. So here's our 1.5 degree scenario. Here's our 2 degree scenario. Put on here, well, we need to remove this wodge of CO2 to keep it, to get us back down to 1.5. If we want to balance emissions, essentially we need, and keep the temperature stable, we effectively need to remove it. And what I'm going to show you in a bit is that that at least in the famous model, and I think that's generally true actually, it's all very fast. Okay, so the question we're framing this in is, what is the consequences of going up, staying up, and then coming down again? And so we do this with essentially some pulse designs, and we look at this relative to two different scenarios, two different background states. And it turns out those background states matter, which has some implications for the robustness of our results. So we did two cases. So one historical case where we let CO2 and other greenhouse gases, but not aerosol, sorry, just CO2 ramp up as observed, emissions. And then we set those emissions to zero indefinitely. So that's our reference case. We then add a positive CO2 pulse, ranging in size from 250 gigatons or petagrams of carbon to 1,000 petagrams of carbon, so pretty large. And then sometime later, we have a negative CO2 pulse, which removes that. So afterwards, we essentially we're back, we think we should be back here if everything was well behaved. I'll show you that it is not far from well behaved. So that's the basic design. So what's our expectation? So we'd expect our temperature change is proportional to the carbon pulse size. So if and linearly proportional to that. For sea level, there's a sort of simple two-level model. We'd expect volume average ocean temperature and thus static sea level rise to behave like this expression. So the deep ocean temperature, the volume average is K1 minus E to minus gamma T, where K is the constant surface temperature, which is essentially dependent on the sensitivity of the model to total carbon emissions, and gamma is the time scale of the deep ocean. So you can see in the infinite time scale, we end up with the deep ocean temperature being the surface temperature, which is well, the change in deep ocean temperature being the change in surface temperature, which was what we expect. So that for gamma T small, we can linearize this, and we essentially see that the volume average ocean temperature is K times gamma times T. So we then expect that sea level rise grows linearly with time during the overshoot, where at this temperature K during the overshoot. And then afterwards, when we remove it, we essentially expect to see it exponentially decaying back to zero, with, again, timescale depending on gamma. Okay, so that's what we expect. So we expect essentially in the overshoot, linear rise in sea level with time, exponential fall afterwards, constant temperature during the overshoot, or with some maybe transients at the beginning, and then return to zero afterwards, again, maybe with some transients. What happens? So we're using the famous model. Famous is a very fast model. It's a reduced resolution version of the HADCM3 carbon cycle model from the early 2000s. So it's fast. It allows you to do lots of experiments and run them for long times. It doesn't have, for example, nitrogen limitations and things like that. So I would expect the details, like in any model, are probably wrong, but I think the broad general picture is correct, even if the exact numbers aren't. So what do we see happen? So I'm going to first of all show carbon. So this is what this plot is showing. Reds are where we use the historical as reference. So that's essentially a scenario in which CO2 emissions follow what we think happened till 2020, and then are zero after that. And blues are where the control is referenced, and the control has no emissions. So you could think of those as a sort of hot end and the cold end of reality. And then we have three different drivers. We have 1,000 petagrams of carbon historical, 500, 250 petagrams, so red, brown, reddish, orange, and then similarly for the control, 1,000 petagrams for the control, 500 petagrams for the control, 250 petagrams for the control. Okay, so what does this show? So the gray line here is the pulse is put in over a decade. And what this shows is atmospheric CO2, as you might expect, rises very rapidly. In the control one, it sort of peaks at 900 petagrams of carbon in the atmosphere, so that's the difference, or in parts per million, that's around about 240 or so. And in the, with reference to the historical simulation, that peaks at closer to 1,000 petagrams, less of the carbon goes into the ocean rapidly. And then atmospheric CO2 essentially declines in both cases. You can look at the other cases, and again, you'll see that in general, regardless of the size of the pulse, the reddish lines are always above the bluish lines during this. So we have this slow decline, and then these gray shades show when CO2 is pulled down. This is after 50 years, this is after 100 years, this is after 200 years. I'll talk mostly about the 200-year case. Okay, so what happens after carbon is pulled down? Well, actually, what we get is we get negative atmospheric CO2, well, net reductions in CO2 below the baseline scenario, which then slowly recover. This is larger in the control with the control references. And it's also larger with time. What's going on and why? Well, here's the ocean carbon, and what you can see is in the pre-industrial control, the background, essentially the ocean takes up more of the carbon. So it takes up more to start with. That's the sort of difference, and it takes up more of it, and then it slowly degasses it. So it takes quite a long time so particularly on the 200-year separation, it takes a long time for this carbon that's in the ocean to come back in. So the other big component of carbon is the land, and the the historical cases of like the world we're in now, we actually see that land carbon goes negative in response to the atmosphere, and I'll explain a little bit about that once we look at temperature. While in the control case, so that might be the cold case, land takes up carbon, and these aren't negligible. There's a sort of rapid loss to start with, and then a slow recovery essentially, but it doesn't really recover completely by the time even 200 years down. The various cases where they drop, again, you can see some time scales, but then things are a few hundred years after this, things are roughly back to normal. So land is not negligible in this case, and I suspect the science embedded in the model in the land carbon cycle is the weakest part of the model. Okay, so that's where the carbon goes. So most of it actually stays in the atmosphere, but the oceans do take up some, as do the land, more into the ocean on more times than the land. And then there are differences, sign differences between the historical and control cases. So what's going on? So we look at forcing. So forcing is the log of the ratios of the CO2 concentrator, or is proportional to the ratio of the CO2 forcing, CO2 cases. And you can think that the surface air temperature will respond quite rapidly to the forcing because the heat capacity of this upper ocean is fairly small, and the transport of heat into the deep ocean is essentially balancing out the fact the reduction happens. So to first order, we can imagine that surface temperature is proportional to forcing with a lag of a few years. So here's the forcing, and you can see actually, if anything, the forcing in the historical cases, the control cases, is actually larger than in the historical cases, even though there's less CO2 in the atmosphere. And that's because the reference concentrations are different. And so it's essentially CO2 is fractional change not absolute, not difference. And so even though there's less of the carbon goes into the atmosphere, because this is relative to a smaller reference value, it has a larger forcing, a bigger change in the energy driving the climate system. Okay, so you can see that it's broadly constant, it's slightly declining in the historical, broadly constant actually in the modern era, because go back here, essentially this is even though it's declining, this is essentially because our control pulse is dropping off as well. What else do we see from this? We see that when CO2 is reduced, is drawn back down again, we end up with negative forcing. And that this is a lot stronger in the control case and the historical case, again, because relative to the background. So what that implies is essentially that the time to get the carbon out of the ocean leads to there being less carbon in the atmosphere. We're drawing it out faster than it can come out of the ocean, essentially, and out of the land. And that means that our concentrations are reduced, and so our forcing is negative. That generates cooling. That actually turns out to matter quite a lot to long-term sea level. But again, we do return that negative thing is weaker in the against the historical cases. Here's the surface air temperature. So in the because forcing is relatively constant, there's actually, you can see very rapid response. So this is trying to show here's the pulse going in, essentially reach temperature, then a slow warming in the historical case. Again, that's because forcing is relatively constant, I think. CO2 pulse is decaying away in the control, dropping in the control historical. So that kind of picture. But I would say that's good enough. That's within 10-ish% or so. So we basically have broadly stable temperatures within 10%, and they occur very rapidly. The time scale for this shift is small. So if you were a discounter, you would be quite concerned that essentially the price of carbon has an impact pretty much immediately. It's not a long-term problem in this world. And then you see these very large negative drops when you draw down rapidly at the end. They're fairly linear in that. Just to show another variable, this shows ice area. That is essentially behaving like surface temperature. And I could show you lots of other things. They all behave like surface temperature. And it's not surprising. Famous' resolution is quite low. It can't really generate anything terribly interesting beyond that. Okay, so that's the surface response. So I did make this point. Response after drawdown does strongly depend on reference case. So question why? Are the time scales different? Is carbon take up and their carbon amount take up and time scales different? So I essentially fit some simple exponential models. So I'm fitting a model that looks like y equals e to the t over k, taking account the sign. This essentially shows the intercept. Red is the historical 1,000 gigatons of carbon, 200-year separation. So that's this is the positive end of the pulse, and the pale colors are the negative. Blue is the control. So we can see as a fraction that we have 900 petagrams here. So less of the carbon makes it into the atmosphere. When we draw down, so this is in the period of drawdown, the impulse is essentially pretty much the same carbon reduction when you draw down. And you can see differences. So less is stored in the vegetation in the historical case compared to the control. And so it draws, it is less negative here. But the soil, which the reason for this is well, soil overwhelms this. So in a warmer world, the soil loses carbon, and that's what the model does, which leads to some big differences in the land carbon. So a lot of what's going on, I think, is explained by the response of the soil and the vegetation to climate change. So the soil loses carbon in a warmer world. The ocean carbon, they're a little bit different. That's what this is showing. They're not terribly different on the drawdown. The timescales seem somewhat asymmetric. On the upwelling, they're quite long. They're long, 100 plus years. I think that actually reflects they're nearly constant. On the down, the negative drawdown, they're quite even longer, effectively constant. Vegetation, and the ocean. So actually, in terms of carbon, it looks like the ocean carbon timescales are the shortest of everything. I think that actually reflects that they're mostly constant. Okay, what about drawdown? So similar changes in atmospheric carbon. Forcing is carbon is larger when the reference case is less. So our forcing is proportional to log C over C reference. So this negative forcing then impacts surface temperature quickly, negative temperatures, or relative to the baseline and sea level, and we'll come to that in a minute. So here's the ocean average temperature. So this is plots of volume average ocean temperature, same idea as before, same color. So blue is the control reference, the cold case. Red is the historical, the warm case. It's actually a little bit less warming, not very much, in the volume average ocean temperature in the historical versus control. Here's when it's emitted, and then this is drawdown at 50, 100, and 200 years. Bunch of scenarios. The thing is, I want you to take, I'll explain a bit more, is I'm going to focus on this period, and then I'm going to talk about this period normalized so we can see the timescales more clearly. So this is showing the emission times the time, ettograms of carbon per year. And if my argument about linearization is correct, we'd expect that to be very linear. So that's what this shows. That's what we'd expect if it was linear. The colors are what we get. And I think that's not far off. A linear out to 180 years, which is essentially from here to here. So I think to first order, it's not unreasonable to say that steric height in the oceans is linearly proportional to the time, the amount you're above, how much carbon you emit in excess, the climate settler, the transient climate response to equilibrium of the system, which is unknown and very uncertain, and the time scale of which you are in overshoot for. So basically, bigger is worse when it's linear with that. So I think that's interesting. So I think we'll come back to consequence of that. The other thing is, here's the post drawdown. And the thing I want, this is a logarithmic scale, and I've normalized this essentially by their average change round about here. So they all start around about 1 and fall away. The thing I'd like you to notice is in the historical case, they're much slower. We're still over about half the response, while in the control cases, that is zero carbon, zero anthropogenic human emissions, they fall much faster. And the reason for this is back to this negative forcing. So in the control cases, forcing is small. The negative forcing falling from when you draw down because the ocean can't put the carbon back into the atmosphere fast enough generates a negative forcing, which in turn cools the ocean down and gets rid of the sea level rise that you went. While in our current world, sea level rise is essentially still there 400 years out. It's not all the cases run 400 years beyond them. So that's essentially the key point. So I'm going to last thing. Good, I've got this amount of time. Here's long-term post-drawdown response. So this is the last 50 years, around about 500. This shows temperature. It's fairly blocky. Here's Africa, South America, North America, Eurasia. It's actually easier to see in a zonal average. So this is a zonal mean temperature difference. Gray is some estimate of the variability. Again, blue, and you might think of this as nonlinearity. That is, we've put the system through a cycle of up and down, wait a long time, how much different are we? And essentially the point is, in at least the big control case, so the 1,000 petagrams of carbon injected into a world with no carbon emissions, we end up with a nonlinearity. And you could just about see that here in the warmer cases, the weaker. So I think that suggests there's a possible shift of the temperature gradient between the hemispheres, which is irreversible as a consequence of going through that up and down case, even if everything else might well look on average normal. So don't quite understand why this is. One expectation of this, and Famous sort of shows it, but it's a very noisy signal, is you'd expect to pull the ITCZ further south as a consequence. Okay, so I'm going to summarize, and then it's question time. So famous surface temperature, and famous is a very low resolution model, responds very rapidly to carbon pulses within a few years. The response is proportional within about 10% to the size of the carbon pulse. Okay, so that I think says that when we think about emissions and drawdown, the response is rapid. Surface climate response is very rapid. It's not something that happens 50 years in the future. It's something that happens at most a decade in the future. Volume average ocean temperature, aka steric sea level, responds slowly and leads to a fairly linear rise during overshoot. I mean, you can see some deviations from it, but they're small. Post drawdown, there's quite a lot of sensitivity to background state likely arising from different forcings for similar atmospheric carbon changes. I would imagine those are quite model dependent, and I think they may also be arising from the peculiarities, I'll say it's wrong, but just the way it's represented of the land surface scheme in famous, though a lot of it does come from the ocean. This negative forcing has a big impact on the subsequent evolution. General point, temperature post drawdown brings you back to reference, though with some potential zonal shifts, but sea level is not, which basically implies you cannot return to non-drawdown climate. If you want to get rid of the sea level rise, you would need a long period of negative forcing to cool the planet, which would then lead to negative temperatures below your reference case. If you want to, so you can't with overshoot, you can't basically end up in the same climate. You can in say either in surface temperature or sea level, depending on your trade-offs, but you can't do both. Policy conclusions, emissions have impact now. The fact we are not flying has impact on us now, not on our grandchildren. If we allow overshoot, we'll pay a sea level price as well as continuing cost of climate change. So if we put carbon in now, the longer it's around, the larger the sea level response is, and these sort of odd things with negative atmospheric carbon dioxide wind drawdown. Overshoot has a cost both through damage plus long-term impact. So it's going to have immediate damage from the surface plus essentially the sea level. We finished.
Thanks, Simon. I'll just allow our participants to unmute themselves, but if anyone's got a question, if you can raise your hand in the participant list, I can call on you to answer the questions. And I suppose while people are thinking about questions, maybe I can quickly ask the first one. I think you might have mentioned this, Simon, but the post drawdown negative forcing, is that proportional to the I suppose the maximum positive forcing? What the difference is by the time you get to actually deploying the negative forcing, if that makes sense?
Yeah, I think the negative forcing is, so it's I think it's proportional to time of overshoot and emission of CO2, so the size of the initial pulse. Hang on, tell you what, I'm just going to swap things around a little bit so I can put you in my look at you rather than look at to your side. So it's a combination of two effects, I think. So how much carbon dioxide you put in or carbon you put in the first place, and how long you let it get into the ocean and land.
Yeah, thanks. I think it's fascinating that the hysteresis in the climate, or the non-hysteresis, as you put it. Does anyone have any questions for Simon? Spirios?
Yeah, very quick, Simon, about the LCA, the attributional versus the consequential approach.
Yep.
So my understanding is that you should first use the attributional, find the baseline, and then move towards the consequential approach. Have you some input or insight on this?
I will ask Matthew to give some insight on this one, that I think is beyond my capacity.
Hi, hello. Can you hear me okay?
Yep, Matthew.
Good. Okay. Yeah, I hear that kind of point about the use of attributional, and to be honest, I don't know where that idea came from. that you need to do an attributional assessment first. Really these methods, attributional and consequential, there are two different types of analysis. They're useful for two different purposes, and simply in answer, when you do a consequential study, you don't need to do an attributional study first. You just get on and do a consequential study. So yeah.
The main reason that I ask is because we are in uncharted water regarding the LCA. So just dive in to the consequential approach might have many limitations, like attributional is played safe. That's my perspective.
Yeah, I mean, it's interesting because I think that is why attributional is so much the incumbent method that is still widely used, even though it isn't conceptually the most appropriate method to use for assessments of system-wide change. I think that happens a lot, that the question that's being asked is, what's the total system-wide change caused by deploying this technology? And sort of unfortunately, people often then just go and pick up and use an attributional LCA because they're familiar with it and the software's available and it's understood. So yeah, I think there's an element of that. And I know advocates for consequential LCA will tell you that it's simpler than attributional LCA. I'm not quite sure that's true. But if the question is, what's the system-wide change in emissions caused by this negative emission technology? That's a question that is properly answered by a consequential study. And an attributional might be out by a considerable amount. Yeah.
Thank you so much.
Okay. Thanks.
Does anyone else have any questions?
Matthew has a question. He asked about tipping points. Matthew, do you want to speak it aloud, or shall I find it and say it?
Sorry, yes, that's just come in. Sorry, I can repeat the question if Matthew doesn't want to. So he's wondering about tipping points. It seems temperature is controlled, but sea ice, ocean acidification, etc., will continue. Question mark.
We have had okay. So we find no evidence of tipping points in famous. I mean, in the sense of a very dramatic change in the system behavior. I think we find evidence of nonlinearity, but I don't think there are tipping points that the system goes into another state. And okay, yeah, zonal asymmetry is maybe a tipping point, but it's a pretty weak one. You asked about ocean acidification. That, yes, again, overshoot is going to generate ocean acidification. And what we find, I haven't shown it here, is that when we draw back the carbon out of the ocean, essentially when you do the negative side, the carbon in the deep ocean is rather recalcitrant. But the carbon in the upper layers actually, again, reduces below the reference case, which I guess would be alkalinization. And I have no idea whether that's good or bad for life. I imagine it isn't, given they probably tolerate a limited pH range. On the other hand, they're probably just going to go back to somewhere around about 1900, 1950. So I think maybe the point to take away is that, I mean, it might well be our experimental design, but if you do very rapid drawdown, in effect, the deep ocean, and you waited a while before you do that, the deep ocean has taken up a lot of carbon, and you can't get it back out again very quickly. And so you pull the carbon where you can, which results in essentially negative relative to your baseline. Did I get where you wanted, Matt? So I'd say no evidence of tipping points in famous. But to be honest, I've never seen any climate model or system model of moderate complexity generate tipping points. It just might say they're missing the processes which generate them.
Thanks, Simon. Olivia?
Hiya. Can you hear me okay?
Yep.
Thanks for the talk, it's really interesting. So you mentioned about the degassing of CO2 once it's gone into the ocean. Does your model also include sort of CO2 that might get buried or stored, or did it release all of it?
Yeah, there's no geological processes. I mean, the ocean model itself, I think, has a sort of fairly limited representation of phytoplankton, and plankton, and organic detritus.
Okay.
But yeah, it basically falls and redissolves into the ocean. But unless, I think the timescales for removing carbon from, let's say, the ocean to the deep ocean to the geological system are very long, 100,000 years. So
Yeah.
we wouldn't see them in these simulations.
Okay, thank you.
Any questions? Still a little bit of time. Phil?
Phil's got one. That's what you funded, Phil.
I think you're still on mute there, so if you... Oh, yeah, we can see you now as well. Hi, Phil.
Oh, hi, great to hear that. One sort of fairly obvious query is the behaviour of ice sheets and that over the timescales that you've got. And I don't know how well Famous deals with how it compares with other models for ice sheet stability, and that's a pretty obvious tipping point.
That's a good question, Phil. There are no ice sheets in Famous that can tip. I mean, the key issue is, so if the ice sheets behave like cubes of ice and just melt slowly, then I think the same analysis we've done for the deep ocean will hold. That is a linear rise. If, as we're concerned about what's happening in Antarctica, they have rapid feedbacks, then essentially they'll respond to surface temperature, so it'll be very rapid. I think the answer, but Famous doesn't include that process.
Thanks, Phil. And I suppose we'll give the last question to David. So if you can unmute yourself. So, David, I think if you're trying to ask a question, I think you're still on mute there. So, to unmute yourself, there's a button in the bottom left. Yeah, I think you've got it now. Great.
Yep. Good afternoon. When I first heard the word accounting, I misunderstood. It seems that you're talking about accounting in terms of physics, where the carbon is going and staying and coming back. You're definitely not talking about financial accounting. And if you were, I would ask you why you had omitted externalities, Dasgupta type of accounting.
I will ask my colleague Matthew to comment on that. I am definitely not an accountant. I'm a physicist. I believe in counting molecules and atoms of carbon. Matthew, do you want to respond to David's point?
Yes, thanks. So, I mean, the term carbon accounting, we did a literature review, and that term is used to refer to physical carbon accounting. So the unit of measurement typically is tons or kilograms or petagrams of carbon, CO2, different greenhouse gases. And that was where most of the discussion in the literature exists. So the issues that come up under the label carbon accounting or accounting are mostly to do with measurement and estimation. So it's things like life cycle assessment. How do you measure the change in emissions caused by deployment of a technology? And I mean, there's a bit of discussion in the literature, or quite a lot, on things like the marginal abatement costs, or the marginal costs of different technologies. But I mean, we briefly touched on that in the paper, but most of the issues that get discussed and we thought warranted some discussion were on the physical carbon accounting rather than the financial carbon accounting side of things.
Thank you.
Okay, thanks, David. And we've got, I suppose, time for one more question, and it's from Rob in the chat. And I suppose I just repeat it. He asks, I think the projections about permanence of storage, tree seed storage is correct for production forest. This is likely to be less so for natural forests, which are not harvested, as in forests maintained for biodiversity conservation. So secondly, will land carbon uptake be altered if large amounts of GGR for negative pulse are land-based, i.e. reforestation of permanent and harvested forests?
So let me have a stab at the first part, and then let's see what I can say about the second one. So the first part, there's two issues. I think in some ways leaving natural forests alone wouldn't be a net. That is, they're not negative emissions, they're in balance. And actually, in a warmer world, they may be a positive emission, because what we're seeing and what the model shows, and I think it's plausible. I think the magnitude is uncertain, but the mechanism is plausible. But essentially, in a warmer world, soil carbon has a shorter lifetime, which results in emissions. So, for example, mid-latitude forests, in famous, the lifetime is order 30 years or so. If you increase the temperature, the bugs go wild and chomp away, and the lifetime goes down. And so you actually, in the short term, get a release of carbon from the soil. So that's, but you can think of that as a carbon feedback, actually. But nevertheless, that's, that needs some thought. So I think it seems wrong to think of as natural forest, as forest left alone without any intervention to grow more, as a negative emission. They're essentially bad. They're going to just behave like this natural system. Your second, do you want to come back with me on that, Rob, before I have a go at your second question, which I might actually ask? Doesn't sound like
Sorry,
it.
they're struggling to find the unmute button, as usual. Yeah, that is true. I hadn't thought of it in that way. I was really thinking of the removals from harvesting.
So you don't get
like.
the issue, yes. Yeah. So if you
Yeah,
planted them and then left them alone, still think they're not permanent because they can burn down or bugs can come along.
Well, indeed, I meant to type that and forgot. So yeah, disease and obviously environmental change in that way, increased drought, that kind of stuff. It does have an issue there. But I was really thinking of establishment of more forest into the future as a negative emissions technology. So land use change based, and wondered how that would affect the land carbon uptake and release into the future, rather than so your pulse and removal would be partially due to natural systems.
I think I think it's quite hard to get very big amounts of carbon out of land use change, and
absolutely,
Matthew
it's only
well
going to scratch the surface.
Comment.
Yeah, it's only going to be about 15% of the total. So
so it's not a permanent store, and there may well be, because essentially you push the price of food up by doing that. So it depends what you've used for, what the land was otherwise being used for.
Indeed, you've got to trade it off with food production, but in large parts of the world that food production is very inefficient, so you could free up land by making your food production more efficient. But it's easy to say that, not so easy to do it.
I'm not sure.
Thanks, really interesting talk.
Thanks, Robin and Simon. But I think we're going to have to leave it there. I know Simon's got a hard stop at the hour, so we do have to wrap up now. But yeah, I'd just like to say thanks everyone for coming along to the first one. We've got the next webinar will be on Wednesday next week. So please do register for that if you're interested in thinking about soil carbon. So I suppose it is similar sort of theme to the final question there. So do come along to that. And once again, I'd just like to thank Simon for his insights and presenting the upcoming project. So thanks, Simon. So, and yeah, thanks everyone and have a good day. Bye for now.